We're going to talk about the properties of inverse trigonometric functions and how they relate to differentiation and integration. First off, let's talk about the inverse of the sine function, written as y equals arc sine x, as you can see on line 1. Now, the original sine function is not 1-to-1. But if we restrict its domain to the closed interval from negative pi over 2 to pi over 2, the range is still the closed interval from negative 1 to 1. By doing this, the sine function becomes 1-to-1, which means its inverse arc sine actually exists. The domain of arc sine is then the closed interval from negative 1 to 1, and its range is the closed interval from negative pi over 2 to pi over 2. Composing the original function with its inverse gives us the identity function, as shown on line 3 and the bottom line. Pay close attention to the restriction on x here. On line 3, the variable x starts in the arc sine function, so x must be in the domain of arc sine, that is the closed interval from negative 1 to 1. On the bottom line, the variable x starts in the original sine function, so x belongs to the domain of sine, that is, the closed interval from negative pi over 2 to pi over 2. Lines 2 and 3 on the screen show a quick calculation rule. The first equal sign converts it to a coterminal angle, which gives us the second equal sign. But 2 pi over 3 is not in the target range of negative pi over 2 to pi over 2. So, we need to convert it to another coterminal angle, as shown on line 3, which brings us to pi over 3. Also, arc sine of 2 on the second to last line is undefined, since 2 is outside the domain of arc sine, which is the closed interval from negative 1 to 1. Arc sine x on line 1 can be thought of as an angle theta that allows us to calculate cosine theta, as shown on the bottom line. Since sine theta equals x, that is x over 1, we can set up a right triangle with a hypotenuse of 1 and an opposite side of x. By the Pythagorean theorem, the remaining adjacent side is the square root of 1 minus x squared. That brings us to cosine theta on the last line. Using the right triangle from the previous slide, we can easily find all the other trigonometric function values, as displayed on the screen. We are going to use implicit differentiation to find the derivative of the inverse function arc sine. If we set y equal to arc sine x, then sine y equals x, as shown on line 2. Using implicit differentiation and taking the derivative of both sides with respect to x, we get the first equation on line 3. Rearranging this for dy/dx gives us the bottom line. The first equal sign comes straight from that equation on line 3. The second equal sign replaces y back with arc sine x. And the last equal sign uses the trigonometric function values we worked out on the previous slide. Line 2 on the screen comes straight from the previous slide. Line 4 replaces y with arc sine x, giving us the derivative formula. And right below that, we also get the indefinite integral formula shown on the bottom line. In this example, we need to find the derivative on line 2. First off, we have to check the domain. Since the domain of arc sine is the closed interval from negative 1 to 1, 3x squared has to be between negative 1 and 1. That means the absolute value of x must be less than or equal to 1 over the square root of 3. The full derivative calculation is shown on the bottom line. The first equal sign uses the chain rule for the derivative of arc sine, and after that, it is pretty easy to finish up. For this example, we are evaluating the indefinite integral on line 2. Using u substitution, we set up u as shown on line 3. The full calculation is laid out across the bottom 2 lines. The first equal sign gives us the new integral after substituting. From there, we cancel out the positive constant a, use the indefinite integral formula for arc sine, and substitute x back in for you to get the final answer on the bottom line. In this example, we need to evaluate the definite integral on line 2. Using the integration formula from the previous slide makes it pretty straightforward to get the answer. The calculation is shown on the bottom line, where we simply use the properties of arcsine to finish up. Next, let's talk about the inverse of the tangent function, written as y equals arctangent x, as you can see on line 1. Now, the original tangent function is not 1-to-1. But if we restrict its domain to the open interval from -π/2 to π/2, the range is still the set of all real numbers. By doing this, the tangent function becomes 1-to-1, which means its inverse arctangent actually exists. The domain of arctangent is then the whole real line, and its range is the open interval from -π/2 to π/2. Composing the original function with its inverse gives us the identity function, as shown on line 3 and the bottom line. Pay close attention to the restriction on x here. On line 3, the variable x starts in the arctangent function, so x must be in the domain of arctangent. That is, the entire real line. On the bottom line, the variable x starts in the original tangent function, so x belongs to the domain of tangent. That is, the open interval from -π/2 to π/2. Earlier, when we talked about the inverse function arcsine, we treated arcsine x as an angle theta to set up a right triangle. By the same logic, we can treat arctangent x as an angle theta and build a corresponding right triangle. Since x is just x over 1, the adjacent side for angle theta is 1, and the opposite side is x. Using the Pythagorean theorem, the hypotenuse comes out to the square root of 1 plus x squared. From here, we can easily work out all the other trigonometric function values, as displayed on the screen. We're going to use implicit differentiation to find the derivative of the inverse function arctangent. If we set y equal to arctangent x, then tangent y equals x, as seen on line 2. Using implicit differentiation and taking the derivative of both sides with respect to x, we get the first equation on line 3. Rearranging this for dy/dx gives us the bottom line. The first equal sign comes straight from that equation on line 3. The second equal sign uses the property that cosine is the reciprocal of secant. The third equal sign replaces y back with arctangent x. And the last equal sign uses the trigonometric function values we worked out on the previous slide. Line 2 on the screen comes straight from the previous slide. Line 4 replaces y with arctangent x, giving us the derivative formula. And right below that, we also get the indefinite integral formula shown on the bottom line. In this example, we need to find the derivative on line 2. The equation on the second to last line uses the chain rule for the derivative of arctangent. After that, getting to the bottom line is pretty simple. In this example, we want to show that as long as x is not equal to 1, the expression on line 1 is actually a constant, and then we will find what that constant is. To prove that this is a constant function, we just need to show that its first derivative is always 0. The steps are shown on line 3, where we use the chain rule for the derivative of arctangent along with the quotient rule. Once we simplify the algebra, it comes out to 0. Since it is a constant function, we can plug in any value for x. The easiest way is simply to set x to 0, which gives us the constant on the bottom line. For this example, we need to evaluate the indefinite integral on line 2. Using u substitution, we set up the variable u, as shown on line 3. The equation on line 4 gives us the integral after substituting. From there, we cancel out the constant a to get the arctangent integral, and finally, we just substitute x back in for u. In this example, we need to evaluate the definite integral on line 2. Using the integration formula from the previous slide makes it pretty straightforward to get the answer. The calculation is shown on the bottom line, where we simply use the properties of arctangent to finish up. We'll continue the discussion on the inverse function of secant, which is represented as y equals arc secant x, as shown on the first line of the screen. The original secant function is not a one-to-one function. However, if we restrict the domain of the secant function to the union of two half-open intervals excluding pi over 2, that is, the half-open interval from 0 to pi over 2, union the half-open interval from pi over 2 to pi. Its range remains from -infinity to -1, union from 1 to positive infinity. At this point, the secant function becomes one-to-one, and therefore its inverse function arc secant exists. Furthermore, the domain of arc secant is from -infinity to -1, union from 1 to positive infinity, while its range is the union of the two half-open intervals excluding pi over 2, namely, the half-open interval from 0 to pi over 2, union the half-open interval from pi over 2 to pi, as shown on the second line. The composition of the original function and its inverse yields the identity function, as shown on the third line and the last line. Pay close attention to the domain of x here. For the composite function on the third line, the variable x comes from the inverse function arc secant, so the domain of x is the domain of arc secant, which is the absolute value of x is greater than or equal to 1. For the composite function on the last line, the variable x comes from the domain of the original secant function, which is the union of two half-open intervals excluding pi over 2, specifically the half-open interval from 0 to pi over 2, union the half-open interval from pi over 2 to pi, as displayed on the screen. When we previously discussed the inverse functions arcsine and arctangent, we could construct a corresponding right triangle. By the same logic, we can also view arc secant x as an angle theta and construct a corresponding right triangle. Since x equals x divided by 1, the adjacent side to angle theta in this right triangle is 1, and the hypotenuse is x. Applying the Pythagorean theorem, the opposite side is the square root of x squared minus 1. At this point, we can calculate all the trigonometric function values as shown on the screen. However, this requires the condition that x is greater than 1, which means y lies between 0 and pi over 2, excluding pi over 2. This slide shows that when x is less than -1, which means y lies between pi over 2 and pi, excluding pi over 2, we obtain different trigonometric function values, as shown on the screen. We will use implicit differentiation to calculate the derivative of the inverse function arc secant. Let y equal arc secant x, then secant y equals x, as shown on the second line. Applying implicit differentiation to differentiate both sides with respect to x yields the first mathematical expression on the third line. Then, rearranging for dy/dx brings us to the last line. From the first line on the screen, we can easily determine the sign of tangent y. The second line shows that if x is greater than 1, tangent y takes the positive sign. The third line shows that if x is less than -1, tangent y takes the negative sign. Therefore, secant y times tangent y can be combined into the mathematical expression on the last line. The mathematical expression on the second line is obtained by combining the results from the previous two pages. Since y equals arc secant x, substituting y into the expression on the second line yields the differentiation formula for arc secant, which is displayed on the last line. This example requires calculating the derivative on the second line. The equation on the third line applies the chain rule to the derivative of arc secant. From there, The last line is straightforward to obtain. This example requires proving the indefinite integral on the screen. Rather than evaluating the integral directly, this proof is established by differentiating its antiderivative, arcsecant. Since x squared minus 1 must be greater than 0, we get that the absolute value of x must be greater than 1, as shown on the first line. Therefore, the proof is divided into two cases: x is greater than 1 and x is less than -1. First, assume x is greater than 1, as shown on the second line. The differentiation process is displayed on the third line and should be straightforward to understand. Next, consider x is less than -1, as shown on the second to last line. Its differentiation process is displayed on the last line. Since the expression contains -x, the first equality applies the chain rule, and the remaining calculations from there are fairly easy to follow. Since the derivative of the antiderivative is equal to the integrand, the indefinite integral formula is thereby proved. By setting up the variable substitution for u as shown on the first line, we can similarly prove the indefinite integral formula on the last line. This example requires calculating the definite integral on the second line. Its first equality directly substitutes the integration formula obtained from the previous page. Then, by applying the properties of arcsecant, it is straightforward to arrive at the final integral value. Additionally, there are three other inverse trigonometric functions, as shown on the screen. The first is the inverse function of cosine, arccosine, whose domain is a closed interval from 0 to pi. The second is the inverse function of cotangent, arccotangent, whose domain is an open interval from 0 to pi. The third is the inverse function of cosecant, arccosecant, whose domain is the union of two half-open intervals excluding 0, that is, the half-open interval from -pi/2 to 0, union the half-open interval from 0 to pi/2. We can similarly prove the differentiation formulas for these three inverse trigonometric functions, as displayed on the screen. We observe that these differentiation formulas differ from their previously corresponding formulas by only a negative sign.